Suppose that I'm interested in analyzing certain characteristics about roller coasters. So what I did was created a data file where I collected some information about a few roller coasters around the country. So I'm going to go to the data file that's on my computer and load that file. So I'll pull that up in StatCrunch here. And what you see is that it's got some information about the height of the coaster, or how tall the main hill is on the coaster, how long the roller coaster is as far as time, how long does it take to make a circuit, and then the length of the coaster, how much track length is there in feet. So you've got height in feet, duration in minutes, and length in feet. And these are the names of the coasters. So you could go and actually, there's YouTube videos that have points of view if you want to look at what the different coasters are. For Kings Island, I did pull the Diamondback, which is a major coaster there. Also, the Banshee, which is their new inverted coaster. And then I've got some from Cedar Point, some from Six Flags, and one from Carowinds called Fury 325, along with Intimidator. So Intimidator is sort of like Diamondback, but if you're not sure what those coasters are, that's fine. But we want to look at some of this information and see if there's a relationship. So in this case, let's say I want to know if there's a relationship between the height of the hill and how long it takes to complete the circuit of the ride. So under stat, I'm going to go down. Well, let's start with a graph. So let's think with a scatter plot whether we think we should even fit a model. So we're going to put height as the predictor variable and duration as the response and click compute, and you have this graph here. And the idea is, okay, what do you think? Do you see a pretty clear linear pattern in the data or not? So you've got a couple of points here, and then it goes down a little bit from there, and then up a little bit, and then these are all spread out. Okay, so the middle somewhere in here, and then you've got a couple over here. So there's not really a real solid linear pattern there. I'm not sure that there's a significant relationship, but we can go back and actually check that formally. So under stat, I could go down to regression, and I'm doing what's called simple linear. So I've got one predictor variable, and that would be the height, and the response variable is duration. And then it automatically defaults to checking for it really checks the intercept, but we don't do that test, just checking if the slope is 0 or not. And then you can also come down and look at other things. We're going to go ahead and do the fitted line plot, make sure that it's given. You can also do some other stuff, and then we'll put a title. So we'll say duration based on height for roller coasters. Click compute, and notice it's going to give you some of the descriptive statistics first. Okay, let me move these graphs around a little bit, so I'll move the scatter plot over a little bit. So if we remember, we're going to look at the slope road. Now the correlation coefficient is 0.35. Okay, so what that tells me is there's a little bit of a positive relationship, but it's not real strong. Okay, the R squared value, you're only explaining 12.4% of the variability in duration when you know the height of the first hill. So you're not explaining about 1/8 of the variation, or why the times are different if you know the height of the first hill. That doesn't seem to be a major factor that gives you a lot of information. Now I can look at the fitted line plot. Okay, so it's going to be the same scatter plot with the line of best fit drawn on it. And even though it looks like it's got a positive slope here, keep in mind that's going to depend upon how spread out your y-axis is and your x-axis and stuff. So this really goes from a low of, what's that, about 2.4 minutes up to a high of, less than 3 minutes. So there's really not but a few seconds difference in here over the course of going from about 100 feet to 300, 325 feet for the height of the first hill. So, you know, there probably is not a whole lot of predictive power in this model, is what this suggests. So as a result, the p-value is not going to be small. So I'm going to end up failing to reject the null. So I'm going to say there's not significant evidence that there's a linear pattern between the variables. So if I were doing if I asked for the correlation coefficient, right, you'd give me the value of R, 0.35 or 0.353 if you rounded it off to 3 digits after the decimal point. Now if I gave you the R squared value and then ask you to give me R, you have to take the square root of this number, and then you know it's positive because this slope is positive, or the line of best fit was positive in our fitted line plot. It's increasing as you move to the right, or the t-stat is positive, right? So there's lots of different ways to know that this would be positive 0.35 instead of negative. If we did the hypothesis test under the null, we would say one of those things, right? Either, so we've got our variables up here if you forget, or you can read them off of the scatter plot, duration and height. Or, you know, the fitted line plot also is going to have duration and height listed. So there's lots of different ways you can find the variables, but basically we would say under the null, duration and height are not linearly related, or duration and height are not correlated. Under the alternative, we're going to say duration and height do have a linear relationship, or they are correlated. Our decision rule would be something like reject the null hypothesis, h sub 0, if the p-value is less than or equal to, and then since there's nothing given, we'll just use a 0.05 level of significance. The test statistic, you could write R equals 0.35 or 0.353. You could also write the slope t-stat, right, 1.359. Or the f-stat, 1.848, if you rounded those off, right? Remember, there's 3 different ways of looking at the data, and they're all sort of equivalent. Okay, now in the homework in iMath, it asks you for the R value, so you'd be writing the 0.353 or 0.3528 number. On the test, I would accept really any of the answers that are available. I'm probably not going to give the ANOVA table though, just to save a little bit of space. So probably the correlation coefficient or the t-stat value would be what you'd have to report as the test statistic. The p-value is 0.1972. Now 0.1972 is not less than or equal to 0.05, so your decision would be fail to reject the null hypothesis, and if you fail to reject the null, there's not evidence of the alternative. So in your summary, you would say using a 5% level of significance, there is not significant evidence to conclude that a linear relationship exists between duration and height of roller coasters. Okay, so I'm going to go ahead and close these out. So what about height and length of track? Okay, do taller roller coasters tend to have more track associated with them? Okay, well again, let's start with a scatter plot and see what you think. So height as the predictor, length as the response. Click compute, and now what do you see? Okay, other than this one that seems to be unusually low in length for the height, because most of the heights are up here, you tend to see a pretty good linear pattern there, except for this one point. So this would be sort of an outlier, and this you can actually highlight it, and you can see that's the Griffin at Busch Gardens, and that might be something related to the space that they had to put the ride in or something. So they made a fun ride, but it was shorter, or it may be, okay, the way it was constructed, it had a decent size, 205-foot height, but yet maybe it moves a little bit slower for some reason. So, reasons why things seem to stand out is a different question than whether you should fit a line or whatever. But let's go ahead and fit a line through here and see what it looks like. So I'm going to actually go ahead and close this scatter plot because we'll have the line of best fit. So under regression, simple linear again. So I'm going to have the height versus length this time. And go ahead and make sure I've got the fitted line plot. And for now, I'll just click compute. I'll come back in a few minutes and do some other stuff with this. Now in this case, we see that the correlation is 0.792 or 7923, right? So that's almost 0.8. So that's getting pretty close to positive 1. The R square is 0.628 or 0.6277. So you're explaining almost 2/3, somewhere between 3/5 and 2/3 of the variability in length of track is somehow related to, in a straight line manner, the predictor variable, which was height of the coaster, or height of the main hill on the coaster. Now, you could also look at the slope and notice the t-stat is positive 4.68. Now, anything over 3, right, positive or negative really in magnitude, that's really far away from the center of the t-distribution, which has a mean of 0. So that's going to be strong evidence, okay? And you actually see that the p-value is very small, 0.0004. So again, we could go through the hypothesis test. So let me go ahead and show you the line of best fit here. So this is the line of best fit. So you've got length and height as your two variables. So we could say under the null hypothesis, length and height of roller coasters are not linearly related, or you could say are not correlated. And then under the alternative, we're saying that length and height of roller coasters are linearly related or are correlated. The decision rule would be to reject the null hypothesis if the p-value is less than or equal to 0.05 for the level of significance. We'll just use that as a default. The test statistic, I would probably report the correlation as being 0.792 or 0.7923 if I round it off. I could also have reported the t-score, t being 4.68 or 4.681 or however many digits are asked for. The p-value is 0.0004. So what this says is if the null hypothesis were true and there weren't a linear pattern, the chance I would see what I did in the scatter plot basically shouldn't happen, right? The probability of that pattern happening if the variables are not related in a straight line manner is really small. I would only see that about 4 in 10,000 times I repeated the study. So the idea is there is overwhelming evidence that we should reject the null, and then we would conclude in summary at a 5% level of significance there is significant evidence that height of the coaster is linearly related to length of the coaster. Okay. Again, the correlation is positive because there's an increasing pattern. As the hill gets higher on the coaster, the length of track gets longer. So there's a positive relationship there. The R square, okay, 62.77% of the variability in the length of track of a coaster can be explained in a straight line model with height as the predictor. That leaves, okay, 1 minus that number, right? So 0.3723, or you could write that as a percentage, is the variability in length of coaster that is not explained in a straight line model with height, and therefore we say that is due to random error. That's your random variability. Not every coaster of the same height is going to have the exact same track length. Some of it is unexplained. That's that natural variation. Now, what if we wanted to go back and do an interpretation of the slope? Okay, so it's positive. Let's just call it 12.6. Okay, so as height goes up, length, because this is positive, is going to go up, and it's going to go up 12.6 units in length every time height goes up by 1. So I could write that as, for each additional foot in the height of the heel of the roller coaster, the track length increases by 12.6 feet. Or I could go back and do by something else, right? So for each 10 feet in height of the heel on the roller coaster, the length increases by, now I have to multiply by 10, about 126 feet for that total length. The next thing we could do is go back and talk about estimation. Now, suppose that I have a couple of questions that I'm interested in. So I'm going to go back to the edit, because the way to get the predictions is where it says prediction of y, you've got to put in the x values. Now, you can change the level of confidence or the level of significance. We're just going to leave it at the 95% level, and I'm going to put 250 and 225 in. And now what you'll see is that in the output box, not only do you have what we had before, but you now have the predicted values. The line of best fit is the same, but this now has your prediction values. So let's say that there's a new coaster being built somewhere, and we know that the height of the heel on this new coaster is going to be 250 feet. The question is, for this new coaster, how long, how much track would you estimate it's going to contain? Now, because I'm doing this for just a new coaster, just one, I'm going to use the PI value. So I want to pull the prediction interval. So I would say, okay, the prediction interval is this interval, right? 4,147.75 to 6,947.99. So I'll round off to 2 digits after the decimal point. So then my summary sentence might say, I'm 95% confident that for one roller coaster, which has a hill of 250 feet, so I've got that x value, I would estimate the total length of track is somewhere between 4,147.75 feet and 6,947.99 feet. Now for the other number, the 225 feet, let's say that, 10 years ago, 5 years ago, lots of coasters were built which had a height of 225 feet. And I want to say, okay, what is the average, or what is the mean amount of track among all roller coasters which have a hill height of 225 feet? So in that case, I'm going to pull the CI, the confidence interval, because I'm estimating the mean of multiple roller coasters, not just for a single roller coaster. So in this case, I would say, okay, the interval is, and then I would give these two numbers, and then what I would say is, okay, with 95% confidence, I estimate the mean amount of track among all roller coasters which have a hill of 225 feet would be between 4,857.53 feet and 5,607.58 feet. So again, the PI would be for a single roller coaster. The CI is the mean for multiple roller coasters. Okay, and the X value is your predictor value, and the confidence interval is estimating the Y, or the track length in this case. So hopefully this gives you another example of regression, and you have one where the duration was not significant. This one was significant, so we used it for prediction.